6b, I'm going to discuss the use of theorems and derivations and get to the way in which they enable derived rules. So remember that every instance of a theorem is itself a theorem, and that means that if we initially establish that circle is a theorem, and we know that square is an instance of circle, then we know that square can be derived inside of any derivation. So let's take a look at how that might be relevant in a derivation. So let's look at 115. Now, well, there are different ways to do 115. So here's one way. So we want to show if not R, then Q, and so we assume not R. Now, if we were proceeding in the way that the strategy directions suggest, we would then go ahead and show consequent, and we'd assume ID, and proceed from there. But we might realize we don't need to do that. If we look at our derivation, what we say is, okay, we want to get Q, right? If we get Q, we can box and cancel with CD. And we look at the premise, and we say, oh, aha, the premise is a conditional, and its consequent is Q. So if we had the antecedent of the premise, we could do modus ponens, then we'd get Q, and then we could box and cancel with CD. So it would be nice to get the premise. Now what we might realize is, oh, hey, remember we have this theorem that says if Q, then if... We know that this is a theorem. Now, here's an instance of that theorem. Yeah, that's an instance of the theorem. So if we could get line 4, then together with line 2, we could get, oh, I made a mistake. That is an instance of the theorem. We replace Q with not R, and P stays the same. So if we could get line 4, we could do modus ponens with line 2 and 4, and we would get if P then not R, and that would give us the antecedent of the premise, and so then we could do modus ponens with the premise, and we would get Q, and then we could box and cancel with CD. So now we know we can do a derivation of this, and we know we can therefore do a derivation of this, right? So if we were just copying the derivation from the theorem, we'd say assume CD, we'd say show consequent, we'd repeat line 4, we'd say CD, we'd say CD again. Now that in context is not the most efficient thing to do, and I'll come back to that. The point here, and let's not worry about the efficiency right now, is this. I knew that was a theorem. If Q then if P then Q. I knew that I could do a version of its derivation in here, as I've done. And so now we can say 2, 3 modus ponens, which gives us a P then not R, and we can then do the promised modus ponens with the premise, which gives us Q, which gives us the consequent of the conditional, which the consequent of the conclusion, and that completes the derivation. So that's good. That's a way in which we can use a theorem. We can actually redo the derivation. However, copying the derivation of the theorem is kind of tedious, right? Once we've done a derivation of the theorem, we know that inside of any other derivation, we could insert the derivation of the theorem. So if we derive a theorem once, then after that, let's just insert an instance of the theorem, and instead of actually copying the derivation, we could write down the theorem number as our justification. So let's go back and see how that might work in the program. So instead of here we cut from line 3 through line 8, there we copied the derivation of the theorem. But instead we could say theorem 2, which is the number of, I'm going slightly too quickly here. Remember, this is the initial theorem, right? And the theorem number of that is theorem 2. So if we said we want theorem 2, so here it's asking we want an instance of theorem 2. So we need to say, okay, what do we want the z to be? In this case, we want the z to be not R. In this case, we want the y to be P. And so we get if not R, then if P, then not R, without having to do this whole derivation, right? So this is theorem 2. This is a version from lines 6 through 11 of the derivation of this theorem, giving us the derivation of a specific instance. But the thought is, look, let's just compress that all into one line. Instead of repeating the derivation, let's say, look, I know this is an instance of this theorem. So what you can do is go, if you're worried about the justification for this line, go to this theorem and find its derivation and copy it in. And when we say this, what we're saying is we could do that, but we're not going to write the whole thing out. So we can, instead of having 1, 2, 3, 4, let's see, 5, 6, 7, 8, 9, 10, a 10-line derivation of line 4, we can instead get it in one line by saying theorem 2, and then we can say 2, 3 modus ponens. And that's much shorter, right? That's nice. That's good. So initially we copied over the derivation, but that was kind of tedious. So we say, okay, if I've already done the derivation of theorem 2, then let me just cite, as since line 3 is an instance of theorem 2, I'm just going to say, go to theorem 2 and copy its derivation over here. And I'm not going to write the whole thing out. So that's a general principle we have in the in our derivation system. When you have a theorem, you don't have to copy the whole theorem, the derivation of the theorem. Once you've done the derivation of the theorem, then you can insert an instance of the theorem, and you can write down as justification just the theorem number, and you don't have to redo the derivation. And that's nice. So what that looks like here is, we have if q, and then we say here's theorem 2, and then we have we apply modus ponens. And it can be any instance of theorem 2, right? So it doesn't need to be the initial one, as we just saw. It could be if not r, then if p, then not r. Now the thing is, when we put in an instance of theorem 2, if q, then if p, then q, well, there are lots of reasons why we do that, but one of the main reasons is we do it because we already have q, and we are going to then apply modus ponens to get if p, then q, as in this case. This is kind of tedious. It's not as tedious as writing the derivation of the theorem, but it's still sort of tedious. What would be nice is if we could skip line 6 and go directly to line 7, and we can. Note here, so the justification for line 6 is 5mc. So what's happening here? So we make a new rule, which we abbreviate as MC for material conditional. Don't worry about why that's the name of the rule. That's what we're calling this rule. And that rule compresses into one step the two steps on the left. So instead of having to first write down the theorem and then apply modus ponens, we can instead in one step say, take this theorem and this sentence on another line and apply modus ponens to the theorem and the other line, and what do you get? And that's what we get. You get if p, then q. So that's nice, right? So let's take a look at how that works in our derivation system. So here we said to get to line 4, first we said theorem 2, and then we said 26mp. But we couldn't say 2m, we could instead say 2mc. We have to choose, there are two versions of MC, and we have to choose the one we want, and we'll not worry about that right now. What's clear is this is the one we want. And what do we want z to be? We want z to be p. So there we go, and right there's 8, and we got that by doing theorem 2 and then 2 modus ponens. But here we just apply MC directly to line 2, and we get if p, then r. And again, we can then bring in the premise, and minus 1 minus 2 modus ponens. And then that's CD. So we can end up with a quite short derivation. Yeah, pretty good. Simpler, more straightforward in some ways than the initial derivation of 115, or certainly the previous two derivations. It's quicker, and it's also quicker than the sort of standard derivation of 215, where you'd have to do some subderivations. So what are some useful theorems and derived rules? Well, ones I've been stressing. So MC has two versions. This is the one we haven't seen. If not P, you can infer if P, then Q. And also, if you have Q, then you can infer if P, then Q. That's the one we were just looking at, and it's any instance of these. Theorem 21 and Theorem 22 don't have rules, but you can put them in, and these are nice because they let you do things with a negated conditional. In our strategy, our basic strategy, we have to do show on negation. This is using Theorem 21 or Theorem 22. You could put those in and then do modus ponens, and that's a different way of using a negated conditional. So, okay, to be clear, if you're going to cite a theorem as a justification, you have to have already derived the theorem, and if you're going to cite a rule, you have to have already derived the associated theorem. So if we go into the derivation system and we look in the rules, actually let me not do that. Let's look first just at the problems. So we're going to save this problem, and we scroll down and we get to 1101. And oh, 1101 is a theorem, and note it's theorem 1. There's 1102, theorem 2, and so on. Now, lucky me, since I have the instructor version, I don't have to do what you have to do. But if you're going to use MC, okay, then you have to come in here and you have to actually do the derivation. And then it's green. And so this says to enable MC1, and don't worry about what this is. To enable MC1, prove T2. So once you prove T2, then you can use one of the versions of MC. And once you prove Theorem 18, you can do another version of MC. And those are Theorem 21 and Theorem 22. So those are quite handy. And so if you want to be able to use theorems or rules, derive the theorems, and then you can either just insert the theorem or derive the enabled rule. And if we look in rules, here we have our basic rules, but then here, and then there are the chapter 2 rules, which we'll be getting to in our next unit. But then down here we see this rule. There's a rule called conditional disjunction, and this shows you, oh, it's turned on by doing theorem 35 and theorem 45 and theorem 46. So that's quite handy. So that's about derived rules. For now, you might think about doing the derivations of theorem 2 and theorem 18 to enable both versions of MC. And you could also, if you want, do theorem 21 and theorem 22 just to there's no rule associated with them. There's another rule that sort of is a little bit better that we'll get to in chapter 2. For right now, there's no rule associated with those, but you might still find them to be useful in doing your derivations. So that's the end of this video. In the last video, I'm going to discuss the material conditional and why it's called the material conditional, and what's special about our conditional, and what that has to do with continuing on from last unit's video on relevance and validity. So I'll see you there.